So last video we looked at just some of the ideas behind gravity and center of gravity, center of mass, that type of stuff, and how we draw gravitational fields. Now we're going to start looking into a little bit of the actual gravitational mechanics. Now, there's basically two things that we are going to look at, really simple. One of them is stuff that is falling, and the other part is stuff that is going to be at rest. And we'll start with the falling part. Now, the falling part is actually really simple. It's actually technically nothing new from what you guys have been doing before. Basically, what we're going to do is just practice looking at things falling, and of course, when things fall, they of course they accelerate, and you guys have done lots of acceleration stuff already. When things fall, they accelerate at, most people know, 9.81 meters per second squared, and that's the common acceleration used for gravity. And this is often given the symbol of a lowercase g, not a capital G, but a lowercase g. So it's the same type thing that we used for forces. We used the g value in forces for calculating weight and stuff like that. But it's still, we're going to look at basic free fall type stuff, except we can incorporate and just limit it to the acceleration due to gravity. So pretty straightforward. So for example, here, let's just take a little situation here. Have like a little cliff or something like that. No big deal. Okay, so here you are at the top. There you are, and you have a pumpkin. Okay, so there's your pumpkin, and you are going to drop the pumpkin. Okay, and let's say it falls. Let's say it falls for 1.85 seconds, and I want to try and find two things. Okay, we're going to try and find out how far up you are, or the height, and how fast is it going when it hits the ground. Well, there's nothing new here. There's no real new thing, just a limited application of what you guys have done before. So let's look at what we have. Okay, well, this obviously, that is time. It's like, well, that's the only thing I have. Well, that's not the only thing you have, because you also have the acceleration, because you know the pumpkin is accelerating due to gravity. So you also have the acceleration. So you've got acceleration and you've got time. Well, with acceleration and time, you can calculate change in v. So this is your good old-fashioned VAT. The only thing is, we can take that acceleration and we can customize it as gravity. So instead of VAT, we can have v equals gt to calculate how fast the pumpkin would go when it actually hits the ground. So really, once again, it's nothing really new, just more of a specific application for what you guys have already been working. So if we take that 9.81 for gravity multiplied by that 1.85 seconds, we can find that the pumpkin is going around 18 meters per second when it hits the ground. Okay, just that easy. Now, if I want to know the height, well, that's distance. Well, that is how you guys have been calculating distance, and there's no difference here. Distance dTV. You have the time, that's the 1.85, except remember, you need average V for this. Well, you know it started 0, and now you guys know it hit the ground 18, so its average is obviously going to be 9. Okay, so we know the average V is going to be 9 meters per second. Okay, so if we take that 9 meters per second for average V and we multiply that by the time, which is still the 1.85, we can find out that the pumpkin, well, we'll round off. Okay, the pumpkin went around 17 meters. So they were 17 meters off the ground. And that's basic free fall type stuff. So again, it's not totally different than what you guys done before, just looking at basic mechanics, basic calculations for things going in a vertical direction. Okay, all right, well, let's take another question. Let's try something else that is very similar to this. All right, let's try something else here. Let's try this. All right, so I'm going to put up here like that. All right, so I'll draw some legs, something like that. There we go. And get a little hand. There we go. All right, we need Need some red here. There we go. Oh, those are terrible eyes. Well, that's okay. Work with what we got. Okay, so we have Thor. Okay, now Thor is floating in the air, and he's got his hammer, and he takes his hammer, and he drops his hammer, which probably isn't a good idea because he can't fly with his hammer, which means he's going to be falling relatively soon. But the hammer falls to the ground. There's the ground over there, something like that. Okay, and when it hits the ground, let's say it hits the ground going 40 meters per second. So, how far up was Thor when he dropped the hammer? Okay, well, let's just piece some things together. Again, this is basic mechanics type stuff. No big deal. Okay, well, we know it hits going 40 meters per second. Here it was going 0 meters per second. So again, basic simple stuff. It went from 0 to 40. So the change in V was 40 meters per second, and the average V would just be 20 meters per second. And we can use that in our basic kinematics in order to figure out how far up he was. So I have my average V. I need that for distance, but I need my time, and I can use my change in V and gravity to find my time. So time would just be the change in V divided by the acceleration due to gravity. So we've got that 40, and we're going to divide that by the 9.81. So it's going to take just over 4 seconds. And we're looking at 4.08 seconds for it to fall. And then once I've got this, I can find my distance using good old DTV. I will use my 4 seconds for my time. I've got my average V of 20, and I can put those two together, and I can find out that he's, well, we're going to round off a little bit, around 82 meters off the ground. And there you go. There's some basic fundamental kinematics, this type of stuff. So again, with just basic free fall, it's just DTV, VAT, except you know the acceleration is going to be 9.81 for a lot of the time. Okay, but now what we can do is we can actually start customizing this a little bit and figuring out a few other things, because we can incorporate some forces into this as well and see if we can expand on this a little bit. Okay, so let's get rid of this stuff here and look at something else. All right. Now, of course, in reality, when things fall, things do not continually accelerate at 9.81. So when you accelerate at, g equals 9.81, typically this is, close to the surface of the Earth, because as you go farther away from the Earth, the gravitational acceleration gets weaker and weaker and weaker, so it is close to the surface. But this doesn't actually account for drag, and you guys have probably heard of drag before. All right, so I'm going to bring a little picture over here. There we go, something like this. All right, so we have something like this, where we have a ball or a sphere, whatever it is, trying to fall down, and of course, when it does that, we have what's called drag force, and of course, drag slows things down, whether they're falling or a car driving or something like that, whatever it is. In the front of here, like if this ball is trying to fall straight down, in front of it, it's being hit. It's being hit by the air, which is going to slow it down. But not only that, back here at point B, you get a bit of a vacuum being created back there. Okay, so you actually get a bit of a vacuum created back there, which actually slows things down. So here there's sort of like high pressure on it, and here there's sort of low pressure on it. You see these little swirlies, those are called eddy currents that you get from different types of fluids like air. Or if you ever been in a canoe and paddled with a paddle in a canoe or a boat, you see like little whirlpools and stuff like that. Or when a big truck goes by on the street, they will have, you'll see like dirt or debris or some garbage or leaves swirling around. That's these little eddy currents right here. And the better the aerodynamics, the fewer eddy currents you're going to get. And that vacuum back there actually holds back the object. So it's not just the hitting of the air in the front, it's also the vacuum behind, as well as other factors as well. But these two things help to introduce drag force. Drag force is depends on a number of things, but those are like the two big things that actually cause it. If you actually look at the expression for drag force, there's a few things that actually can be actually calculated. If you actually calculate the force of drag, the formula is actually 0.5 CD rho AV squared. And when you have this expression, I'll sort of just go over a couple things with you and sort of explain it. The coefficient of drag is actually has to do with the shape of the object. Different objects have better shapes for going through air, and the better the shape, the better it's going to work. This is actually, that's rho. It's not a P. It looks like a P, but it's actually called rho. It's Greek letter. That's actually the density of the fluid or the air, whatever you want. And depending on how, obviously if the air is denser, it's hard to go through. This A, that's actually the cross-sectional area, or like the impact area of the object. And this is how fast it's going. And you can see it's actually squared. So speed is actually the biggest factor in terms of how much drag there is on an object. The faster you go, you get way more drag. So if you double your speed, since it's actually squared, you'll have 4 times the drag. That's one of the reasons it's, if you're like riding your bike, if you're already going fast, it's way harder to go faster because your speed is so high, and you square it, you got way more drag on you when you're actually driving. So those are some of the factors that are incorporated into drag. And this is sort of like the idea behind it. But basically for what you guys are going to do, this is sort of like, it's sort of like friction. It's the exact same idea as friction, where if you want to know what is the acceleration of a falling object, well, when you guys did like boxes and stuff like that, you guys didn't need any force. You guys needed net force. And what you guys would do is you guys would take the applied force and you would take away friction to find out what the net force is, because that net force is what got you the acceleration. Well, same idea for free fall type stuff. You'll want to know the net force on the object. Well, the applied force for something falling, well, that's just the force of gravity. Gravity is what's pulling it down. And friction for this type of thing, well, friction comes from drag. So that would be the force of drag. So if you know the force of gravity and you subtract the force of drag, you can then calculate your net force, and then you can actually calculate the acceleration of the object. Okay, so it's relatively simple. So suppose in this question right here, we've got the red ball. Okay, really simple. Suppose the weight of the ball, that'd be mg. Maybe there's 15 newtons pulling it down. Well, and then you find the force of drag, and you calculate the force of drag is 3 newtons. Okay, well, all you'd have to do is to find the F net is really simple. Just take the 15, take away the 3, and you'd have 12 newtons of net force. And then you could then use this divided by the mass, and you can calculate the actual acceleration of the ball. So it's a relatively simple idea, and if you've done basic forces and friction, there's pretty much no difference between what you guys will do with this and what you guys done previously. It's just basically air friction. But you can then calculate accelerations of things in different scenarios where it's a little more realistic than things just falling at 9.81 all the time.